All right, we're going to switch gears a little bit. We're still talking about three dimensions. Conic sections don't really look like it. They're based off three-dimensional figures. We talked about those two cones that are meeting at the tip. Now we're going to talk about how to graph in three dimensions. So you've graphed in two dimensions a lot. Most of your math career, you did a number line, that was one dimension, and then you did the Cartesian plane, which is two dimensions. You have x and y ordered pairs. Well, now we're going to plot in three dimensions. So I can plot points in 3D space. I can also find the distance and midpoint of 2 points in 3D space. And I can write the equation of a sphere given characteristics of the sphere. So it's a lot to wrap your head around. If I were you, I'd even just pause the video right now and read this and try to make sense of it in the picture. I'm going to try to explain it, but sometimes when somebody else explains it, it's too fast for your brain to process. But the big one here, the x-axis and the y-axis are now laying flat on the ground, and the z-axis is coming up out of it. Okay, so we're used to having y up and down, x left and right. Well, now it's x, y, and then coming out of that up into space is the z-axis. A point P in space uniquely corresponds to an ordered triple, x, y, z. This x, the first number, tells you how far to go along the x-axis, y tells you how far on the y-axis, and z tells you how far to go along on the z-axis. And where those three places meet, out here's point P, you went over x units, then you went over y units, and you went up z units, and you're floating out there in space, which is hard to do on a two-dimensional piece of paper. So sometimes you start graphing and you don't feel like you're doing a very good job. That's okay, because it's hard to graph a 3D picture onto a two-dimensional piece of paper. So the point x, 0, 0, so any number, comma, 0, 0 is going to be on the x-axis, because you're going along the x-axis and then you're going 0 in the y direction, 0 in the z direction, so you'd just be on the axis. Same thing, 0, anything, comma, 0 would be somewhere on the y-axis. You're floating around the y-axis, that'd be like a y-intercept, and then 0, 0, and then any number means you're on the z-axis, so that would be like trying to find the z-intercept. So eventually tomorrow we're going to give you equations. We want to have you, which equations in 3D typically, we'll talk about powers, will make up a plane. Whenever you did equations in two dimensions, if they were first powers, they made a line. Y equals mx plus b. When we threw x squared in there, that's where things started curving around. We put different powers. But if it's to the first power, it's going to be a flat line. Well, here, if I have an x, or if I have an equation where x, y, and z are all to the first power, you'll have a flat plane, is what we made up. There's also three planes mainly to look at. The xy plane is a plane that has a number, another number, comma, 0. And that means you went along the x-axis, along the y-axis, and you stayed there. So right here is like this plane down here, this flat line, or flat plane, flat surface. That xz plane would be the one kind of going this way right now. It starts here in the corner and goes up. And that's if you have any number, comma, 0, comma, any number. That just means you didn't go in the y direction. You didn't come off that plane. And same thing with the yz plane. The yz plane is like this plane back here. Kind of think of a flat wall back here. If you're looking at the corner of a room, it'd be the right wall over here. So right wall, left wall, and then that would be like the floor down there. So to graph these, take your time. It's not super easy to graph these, but if you use, some of you who are more artistic are probably going to find this a little bit easier than those of us who aren't. I'm going to try to use different colors too. So this first one, it says go 3 in the x direction, 2 in the y direction, 4 in the z direction. So first I'm going to go 3 in the x direction. So x would be 1, 2, 3. I'm out here. Now I'll go 2 in the y direction. Well, in the y direction, it's going to be going this way where those two meet. So think parallel out here, parallel to the x and y axis. So out here is where they meet. That'd be going 3 and 2. So now I'm out here. I'm in the xy plane still. Now I need to go up 4 units. So I need to go up 1, 2, 3, 4 units, but from here. So I'm going to go up 4 units from there. And the easiest way to do this, I'd say go up 4 units here. This is parallel to the x-axis. Come out until these line up. It's almost like you're making a box. Okay? And then come out this way until these meet up. This way, this way. And right there is point A. Okay, so kind of made a box out of it. Not perfect, not outstanding, but kind of made a box out of it. Now I'm going to switch colors so so you can kind of see the difference here. Now for point B, I need to go -2 in the x direction. I'm going to go right 4 units, and I'm going to go up 2 units. So I'll be over here somewhere in this space. So do a lot of parallel lines. So I'm going to go 2 units back, is back here, and then 4 is right here. So I'm just going to do some parallel lines, sort of like a parallelogram where those 2 sides meet. So about right there, and then you go up 2 units. So up 2 units. Let's see here. Where these meet. Yeah, I'm trying to make a box out of this. Two units, right? 2 units back. So somewhere about right there is where B would be, somewhere in that area. Okay, and then the last one, I'm going to use a pencil for here. I'm going to go 2 in the x direction, so that's here. I'm going to go -4 in the y direction, so that's to the left. So 1, 2, 3, 4. You can make a parallelogram out of this. So this is going to be a flat line on this way. This is at a bit of an angle. On this way. About right there. And then you go 4 down into the z direction. So 1, 2, 3, 4. Come out this way. So somewhere, let's say, we're going down, so we're down in here somewhere. So here's C down in that part right there, which looks like you're on the x-axis, but you're actually very much below the x-axis. It's just back in the corner. So it's below the x-axis, but it's tucked back to the left, and so it's kind of hard to see these. But again, and for the most part, you'll have to just pick those out. On Math Excel, you just got to pick out which picture matches up. You don't have to draw it yourself. So that's kind of the nice thing about it. Now, a little bit of math here. So back to some algebra instead of the artistic part that's sometimes difficult. Let's find the distance between these 2 points. So if you remember, the distance was just a glorified version of the Pythagorean theorem. So the difference in the x's plus the difference in the y's equals the distance squared, and square root both sides. Well, here, adding a third dimension just means you find the difference in the third coordinates and square them too. So it's really just an extension of their previous distance formula, which was an extension of the Pythagorean theorem. So what I'm going to do here to find the distance between these two, I'm going to take the square root of, and it's the difference in the x's, plus the difference in the y's squared, plus the difference in the z's squared. So just pick an order, doesn't really matter. You can do this one first, since it comes first. So -2 minus 4, 3 minus -1, this will be a plus, and then 1 minus 5. So this is going to be 6 squared, which is 36, plus 4 squared, 16. That's a -4, but when you square it, it becomes positive anyway. So 16, and that's going to equal radical 68. You can make that 2 radical 17, or you can just put 8.25, depending on what is being asked, which form you're supposed to get the answer. This is probably the one that gives you the most information. They're about 8 1/4 units apart, roughly. Now the midpoint, what point is halfway between these two? it's the same as the midpoint when you're in 2 dimensions. So you take the average of the x's, the average of the y's, and the average of the z's, and those are the x, y, and z coordinates of the midpoint. So this would be, so the average of the x's would be -2 plus 4 divided by 2. Average of the y's would be 3 plus -1 divided by 2. And then 1 plus 5 divided by 2. So this first one, 2 divided by 2 is 1. That'd be 2 over 2, which is 1, and that'd be 6 over 2, which is 3. So the midpoint would be 1, 1, 3. Now, if you think about a sphere, a circle, I'm going to go back to a circle even, because this talks about that a sphere is basically a 3-dimensional circle, being rotated around. And a circle is a collection of all the points the same distance from the center. A sphere is the same thing. A sphere is going to be a collection of all the 3-dimensional points that are the same distance from the center. So if you look at this formula and look at the distance, I want the same distance from the center. So I got to take all the collection of all the points minus the center, and that'd be that distance. Okay, and add all these up. So really, you're just using the distance formula to find a collection of all the points that are the same distance, the same radius from the center. And then just to get rid of the radical, we square both sides. So this, if I cover that up right there, that's the formula for a circle. Now there's a third dimension, so you have to include z, where, x minus h is the x coordinate of the center, k is the y coordinate of the center, l is the z coordinate of the center, and then that all equals r squared. So after all that is being said, if you want to graph this, find the standard equation. Well, it'd be x minus, and this is the h, k, and l. So minus 2 squared plus y minus 0 squared, I'm just going to go like this, plus z minus -3 squared. And how far away do we want it to be? We want it to be 7 units away. Well, since I got rid of the square root, this was a 7, but when I squared both sides, this became a 49. And that's it. You just plug it in. So that would be the answer. That's the standard equation of the sphere that's centered at this point right here. If you have the right kind of calculator, you can graph in 3D. I do have a 3D calculator somewhere on my desk here. Maybe I can find it and show you real quick. Well, I could not find my calculator, but I did find this. If you go to geogebra.org/3D and type that in, it'll show you. You can zoom in and out, and there's a sphere right there. If you want to change the center of this, maybe I want it to be centered at the origin instead. I could change these. Like that. That just changes the center. If you want to change the radius, maybe I want the radius to be, say, 9 units instead. Well, I'll put an 81 in here. That's a little bit bigger. Maybe I want to put a 4 in there. It's going to be a real tiny little sphere. So that's pretty cool if you want to have some fun with that. Go to geogebra.org/3D, and it lets you graph in 3D, which we'll do more tomorrow.